because otherwise we have to we started a little bit late, I think.
Now you hear me. Okay, perfect. Good. So then again, for the recording, thank you to the organizers for inviting me and for just having this wonderful event. Okay, so I'm going to talk a little bit about the Poisson boundary. So I will just give some, I don't know, some nice hints why this is an interesting object, and then later some applications. So in particular, so first, I'm just really talking about random walks. That's the plan, random walks on topological groups and their boundaries. So today, this is mainly what we are going to do. We will see definitions, we will see some basic properties, and also we will see why the Poisson boundary is an interesting object just from the viewpoint of algebraic properties of the group. And then tomorrow, I'm going to talk about so-called commensurated subgroups. And explain also Schlichting completion and kind of why this is a somehow interesting tool to understand certain properties of the Poisson boundary. And then in either at the beginning of of tomorrow or then in the third talk, we will see something about Fürstenberg entropy. And very briefly, in the very end, I would like to talk about what we call the relative Poisson boundary. Is my handwriting big enough and visible enough, Pencil? Yeah. Just please feel free to interrupt me whenever there is something you can't read. I know my handwriting is quite sloppy, just interrupt me. Okay, so let's start with the first one. So throughout, or should I say, yeah, whatever. So we consider G being a topological group. So my question is, who does know what a topological group is? Most hands, but not all hands. So just since this is really a winter school and I want to be very basic and maybe even not manage to do all this, but just really doing basics, what does this mean? So it's a group, which is also a topological space. And the group operations, let's say, so G times G going to G, where I have some G1 and G2, is mapped to G1 group operation with G2. This is continuous, as jointly continuous, as well as the inverse. So G is mapped to G inverse from G to G. These two things are both continuous. Okay? In the topology of the group. For technical reasons, I will always assume that G is locally compact. So in particular, there is always a nice Haar measure. And it's separable or second countable. But if you're scared of these things, just, I mean, think of discrete groups. This will be already kind of our most kind of things we deal with and will be already quite interesting. Okay, so, and now on this group, I want to consider random walk. So it's just a probability measure, which I will denote by mu, a Borel probability measure with respect to the topology on my group. And I want to say that this is a probability measure is generating in a sense that it kind of really sees the whole group. What do I mean by this? I want to have the G is generated by the support of the probability measure. If I look at it, it's generated as a semi-group, and I take the closure here. So what do I mean with semi-group? So I don't want to have inverses, but I only allow multiplications. So I look at all the elements in the support. Does everyone know what the support of a measure is? Who does know what the support of a measure is? I'm sure you know. No? Okay. So just support of mu would be the collection of all x such that for every open neighborhood O which contains x, we have mu of O is strictly greater than 0. Okay, and we take all these elements here in the support and we allow any kind of multiplication and we take the closure, and this really should be the whole group. This means that the random walk generates really the group. It's not like there is a closed subgroup which is actually never visited by the random walk. Okay. And also another technical assumption is we assume that it's so-called spread out, meaning that there exists some convolution power such that the measure is absolutely continuous with respect to the Haar measure. So for discrete groups, this is always fulfilled. We don't have to worry about this. So this notion of absolute continuity, are you familiar with that? So this means that if I have some A which is measurable and the Haar measure on some A is 0, then this implies that mu of K of A is 0. Okay? So meaning that whenever I have something which is here a null set, then in particular it should be here a null set. Okay? So there is nothing which is basically not seen here, but it would be seen here. This should not happen. This means absolute continuity. And it's denoted just by 2, this kind of smaller signs. Okay, but this is a technical assumption. Don't worry about this too much. It plays a role for harmonic functions then later, but okay. So we do have now this the setup example. So the most kind of one of the nicest example which you can look at is you look at the free group on 2 generators A and B. So if you want to draw the Cayley graph with respect to these generators, you have something like this. Okay, so and here on this free group, for instance, we can consider the simple random walk. Does someone know what the simple random walk is? So exactly. So we start here at E and with equal probability, I'm going here either to, let's say we have here A, let's say we have here B, and then here we have A inverse maybe, and here we would have B inverse. Can you still read this? No. Okay, but I just write it bigger. A inverse B inverse. Can you read this? Okay, good. So the simple random walk would just be the probability of going either A or inverse A should be the same as the probability of going B or inverse B. And this should be just 1/4. So I'm starting here, and with probability 1/4, I'm going here, or I'm going here, or here, or here. And then when I'm at the next position, again, with probability 1/4, I choose each of the direction. This is one way of defining a random walk. Yeah, we will go back to this example then later, but maybe this just to have it in mind. Another example which I want to give you would be the lamplighter. The lamplighter group just over C. So what is it? So the very mathematical picture would be we draw some lamps. So this is basically C. And some of these lamps are on, others are maybe off. I don't know, maybe here we have on again. And I have a lamplighter. So some guy standing here, and he's walking around and turning off and on and off lamps. So you imagine a street which is just a line, and the lamplighter is going and randomly turning on and off lamps. So formally, what is G? G is the ref product of C modulo 2C over C. So you can think of it as just over C, the direct sum of, so the semi-direct product of this. So this is basically the configuration of so this is 0 or 1, depending on when the lamp is on and off. This is the configuration space. And this is the position of the lamplighter. Is everyone familiar with semi-direct products? Who does know semi-direct products? So so let me define it. So AN, so we have some sequence AN and in C, and some position of the lamplighter, let's say M. And so this is an element here. So I have some sequence. So I have only finitely many lamps are on, the rest has to be off. This is why I denoted it by this sum symbol and not by, this plus symbol and not by a product. And then the Cartesian product just with C, and then this is given by some Bn, the other element, and some K, let's say. And this is just defined. So I'm taking this configuration and I'm adding this configuration, but I'm shifting first here with this M element, this configuration. So the definition of the multiplication of inside here in this group is given as AN plus Bn minus M. So I shift everything by my M. And then again, I run over all N. And then here I just add the positions of my lamplighter. Okay. This is the group operation given for the lamplighter group. Are there any questions so far? Okay, so what would be a nice random walk which we can consider? Well, we can say, okay, we want to have, maybe we want to say, if I take the element which has 0 everywhere, maybe let me just denote it by some 0 or a big 0. And the lamplighter is, let's say, standing at either plus or let's say -1. Then, for instance, this would be 0. This would mean just correspond to walk. So it means that the lamplighter is walking to the right or to the left. This is the walking. And now we have to make some probability so that it's allowed to turn on and off lights. So I have mu of, let's say I have 1 at 0. So this should correspond. So from the notation wise, this 1 at 0 is denote the sequence where I have 0 everywhere. But then at the position 0, I have a 1. And 0s everywhere. So here I would have -1, here I have 1, and so on. So kind of, this is over the integers, I have the lamps, namely 0 or 1. And here at 0, I want to have it on. And also the lamplighter should stand in 0. And so I can, if I just put positive probability on both of these two things, I will definitely have that this will be generating, and I'm fine. Okay, again, the second condition is automatically fulfilled because we have just a discrete group. I see some confused faces. Is there someone who can't read something or some question? So this, yeah, I mean, tell me some better notation. So I just write basically 0, so infinite, just zeros. Just everywhere 0. But yes, thanks for asking. And this would be plus or -1. So it's basically, it's two different values. Okay. Okay, so these are kind of two nice groups to have in mind, which we will come back later. And for those who are bored, can already think of, okay, now I'm defining what boundaries are. And you can think of, okay, in the examples, what will be the boundaries? So the definition, if I have G acting, let's say continuously on some X and nu, X is compact and metric. This is some nice probability space. So nu is a probability measure. Maybe I should write this. It's also a Borel probability measure. You can do all this just for standard spaces, but just for the definition as I write it down now, I need compactness. Can you read all this, what I'm writing down? Okay. Is called, let's say compact mu boundary if the following is fulfilled, namely two conditions. One thing is that it's mu stationary. Meaning that nu is the same as if I convolve with it, with mu. So maybe just to give you the definition, what does it mean? It's a measurable set. It's just the integral of nu when I shift this set by a G element, and I don't only shift it by 1, but I average over all G elements according to my random walk. So basically it's it says like, I'm not starting here at the identity, but I would start at each of these points, but I really average around this thing. And what I forgot to tell you is, okay, what are these boundaries supposed to do? They, to some extent, should, I will write it later, should somehow capture our behavior of the random walk at infinity. But I will give a remark just in a moment. So one thing is mu stationarity, and we will also then later just see what mu stationary things are good for. And don't be afraid of them. Whenever you have a measure which is invariant, actually it's stationary. So all those people who do invariant dynamics, you are all in the stationary world. You just don't know it, okay? And the other thing is mu proximality. And this is why we need compactness here, is that I want to have that for mu to the n almost every sequence Gn in G to the n fulfills the following. Namely, if I take the weak star limit of my measure on the boundary and I push it forward, I will explain this in a moment what I mean by this. Then this really should converge to a Dirac measure at some point, which I denote by boundary of this sequence, where so this boundary of this sequence Gn is really just an element in my space X. And what do I mean here with this notation? So I do mean that, and G nu of some A, we had this also in the morning. So Bachir was also saying it, he denoted it by subscript here. But I wrote it in the same line because mine things are anyhow not very linear. So this is just nu of G inverse of A. Okay, so I'm kind of pushing forward this measure further and further, and I want to really converge to the Dirac measure at the single point. So what does it mean in the picture maybe? So you want to understand this random walk. And so you want to, I don't know, it goes maybe here, then maybe down, then maybe up again, whatever. It goes somewhere. And you always want to, if you restrict it to certain kind of the branches where it is, it really somehow should converge to a single point, at least in the distribution. This is somehow there, maybe you want to have the intuition which you want to have. Okay. So, and if these two things are fulfilled, then you call this space a boundary. So basically a boundary is just, maybe as a remark or so, a boundary is basically a way of compactifying, but let me put this in parentheses because it's not an accurate term, because compactifying with topology, compactifying the paths of the random walk, Okay, so I have a nice random walk, and I want to somehow not only get what the random walk does at some point in time, but I want to understand what does it do at infinity. How is it distributed at infinity? What happens there? And the interesting thing is that often if you look at a group from very, very far away, then actually you understand some important properties, some algebraic properties. And that's somehow the deep thing here, and we will see then later what it is. So what maybe one way also, what I should maybe say, so this boundary point here of this sequence, maybe I should put one more parenthesis here. It's really all depending on the whole sequence here. So what is this boundary map? Is really a map from the space that's denoted by omega. It's the space of all paths. So what is a path in my random walk? So I choose, according to my measure mu, I choose some G1. Next realization would be G1 times G2. Maybe it cancels out and goes back, I don't know, whatever. Next thing would be G1, G2, G3, whatever. And it continues. It always adds one more step. And this is over all my GIs in G. And from this set, the boundary is really a map from this set to X. And it's in particular, there is a nice group action here. And of course, the group action here. And this map is G equivariant. So what is the group action here? And why don't I just take only just G1, G2, and so on? Why do I need to take the product here? Exactly. And so acting here with the group element, let me see where I can squeeze it here. Maybe. So G acting on omega. So it would just be, I have some G acting on this sequence, on this, I don't know, let's call it omega, would be, then I have G and then I have G1. Then I have G and then I have G1, G2, and so on. So this is my action here. And equivariant, G equivariant, does everyone know what it means? So equivariant G, equivariant means that if I have G acting on my boundary on this sequence, what is this point here? Where is this point? What is the action here, what I'm writing? Yeah. Exactly. So this is really, this is the action on X. This is really the action on X. And this is the same as the boundary of this G times and then this Gn sequence. And this is the action which I wrote up there. This is this. Okay, this is what we have G equivariant, meaning if I'm acting here and then I apply the map, it's the same as first applying the map and then acting. Okay, good. Back to the examples. Yeah, question for the more bored audience. Why did I need compactness? Yes, it's measurable. It's equivariant and measurable. Yes. Why did I need compactness? Exactly. So because I have here this weak star limit. Does everyone know actually what weak star limits are? I'm lacking some space. So weak star limit of some sequence, I don't know, let me just call it nu n, would be just defined, would be just defined that you have the integral of f of with respect to this d nu, and this should really converge to the integral of f of d nu. so the integral with respect to the measure for every f which is, let's say, compactly supported. We have compact support on my space. Okay, this is just definition of weak star limit, meaning that if you have so some measures converge weak starly if you take their integral for any functions, and these integrals converge in the usual sense. It's just convergence in R. Okay. So back to the example. In the example of the free group, for the simple random walk, does someone know some nice boundary there? What would be a nice candidate for my space X? What would be a nice candidate for a measure? It's a non-trivial question. It's not so nice to ask. It's basically those people who know, and the others. Okay, so a nice candidate would be here if I take. So what do I want to do? I want to have a compactification of my paths. Exactly. So I just allow this path to be infinite, and I'm done. Okay. This is a way of kind of allowing the paths to be infinite. So I take the collection of all infinite reduced words. So meaning that if I have A and A inverse next to each other, then I don't want to see that. So I should cancel out. This is the collection of infinite reduced words. So yeah, so of the generators of A plus minus 1 or B plus minus 1. Okay. How is the action there? What is the action of G on this space? So we have F2 is acting on F infinity star by yes, exactly. So it's really basically concatenation in the beginning. So if I have here some element omega, then and here then or whatever, some element A, then I start here then at A in the beginning and then this. Okay. Should I write it down more precisely or is it fine? So so meaning that if I have some G in F2 and I have some omega in F infinity star, then I have G times, let's say this omega equals G1, G2, omega 1, omega 2, and so on in F infinity star. Then G times omega is just then the sequence G, omega 1, omega 2, and so on. And possibly also do some cancellations if they do. Okay, because in the end you want to have again an element in F star infinity. Okay. Good. The probability measure, which we will see then that it will be stationary with respect to the simple random walk, is so if I take some cylinder set of elements, I don't know, x1 and so on until xn, where so with the cylinder sets, how do I write it? So this should really be the collection of all, actually I don't need brackets here, sorry. Let's just put away the brackets. X1 and so on until xn, and then I have maybe some y1 and so on, infinite in F infinity star. Okay, so I take all the words, infinite reduced words, with the prefix x1 until xn. Okay, this is all multiplication there. And at this cylinder set here, how do I want to define my random walk? Well, for the first element, I have 4 choices to go. So this first element, sorry, maybe I want to say this. Xi should all be in A plus minus 1, B plus minus 1, and there should be no cancellations. Okay. Then for my first element, I have 4 choices. So I have 1 divided by 4. And now, since I'm not allowed to go back because I have already ruled out all these things, I'm already canceled out the things, I have only 3 choices to go for the next one. So, and for all the rest, I have 3 choices because I'm always not allowed to go back because otherwise I would cancel things out. So I have here 1/3 to the power n minus 1. This is my probability measure. And it's enough to define this probability measure on the cylinder sets. The cylinder sets nicely generate my sigma algebra, so I already told you what the whole measure is there. Okay. So time-wise, yeah, but still no. So let's see that this is mu stationary. I mean, I could also give you this as an exercise, but no one does exercises. So, and it's maybe a good way of getting some feeling for what is going on. So what is mu stationarity now? We want to check this condition, okay? What does it mean? Here in this this integral here, what is it in our setup? Is it still an integral? Can we write it easier? We have now here G is just the free group on 2 generator. It's a countable group. So this integral just translates in something countable. So I have here the sum over all G in my free group of mu of G times, and then I have here nu of G inverse. And let's again take this nice cylinder set, x1 times and so on times xn. And I want to say that here actually, in fact, if I take all this average, then my outcome will just be nu of this cylinder set. This is what I want to check. So what can this mu of G be? What is this mu of G? Kind of here. How many elements does my sum have? How many non-zero elements? Yes, exactly, 4. So this here is, in most of the cases, and I mean infinitely many cases, it's 0. And it's 1/4 only if G is either A or A inverse or B inverse. Okay. So we have just 4 elements here, meaning we have here just, and now let's do already the next thing. So we have 1/4 times, and now I have here the possibility if this cancels out or if this doesn't cancel out. This x1 until xn, they are fixed, and my G can vary between A inverse, B inverse. So it will, in 3 of these cases, it will not cancel out. Okay, so I will have 3 times, and now I look at how is it defined here, this probability. I have 1/4 times 1/3 to which power? So this is the case kind of where it, so G is not equal to x1. What power do I have here? Yeah. Exactly, because I have here now n plus 1 elements, And I have here n plus 1 minus 1. So we have here n plus 1 minus 1. So we have really n elements plus, and now I have 1 times the probability that it actually does cancel out. So meaning if this cancels out, I have only n minus 1 elements left, and I have here 1/3 to the power n minus 2. Okay? And if you now just do the calculations, should I do the calculations? I don't know. Yeah, okay, let's just, because otherwise it's maybe pointless. So what do we have here? So, okay, this cancels, this cancels with, so here I will have my n minus 1. So I have here 1/4 of, then again, 1/4, 1/3 to the power n minus 2. And here I have here one more, so I have 1/4 times minus 1, something, wait, 3 times, enough, something like this, no? Yeah. And so, calculations. Yeah. Yes, no. Do we have, sorry, let's take the 1/4 also outside, then it's easier. And then we have here 1/3. Okay. Okay, so, and then here, so what do we get here? So we have here 4/3 plus 4/3, which then the 4 will cancel out with this. And then in the end, what we have left over here is 1/4 times, and then I have here 1/3 to the n minus 1, which is exactly nu of this cylinder set of x1 times and so on times xn. And this means that actually nu is mu stationary. Okay. Proximality is also similar, maybe just for the time-wise. Mu proximality is just an exercise if you're interested in this. It's also not difficult. Okay. Good. So how about the lamplighter? Lamplighter is a little bit more advanced. But let me just say it briefly. Okay, maybe let me just add here at the lamplighter directly. So if we have that the expectation of my random walk when I project it to C, if this has a positive drift, so meaning that my random walk has maybe, I don't know, it has some kind of weight on one feet and it's more likely to step in one direction. Then what does it mean? It means it's kind of, it turns on and off lamps, but somehow it drifts over to this side, which means that it, at a certain point, it won't be able to go back and change the lamp configuration there. Meaning for a certain time, I really have a stabilized lamp configuration. So mathematically speaking, my space X is then the collection of all lamps where I have finitely supported lamps on the negative, but I allow infinite supported lamps on the positive side. Okay, so here I can have infinitely many lamps turned on. This is my configuration space of the 4x. And nu is just the kind of corresponding heating measure. I won't go too much into details. Maybe a short remark. Otherwise, if we have that the expectation of the projection of C of mu is 0, then it follows actually that we will have just a basically trivial space. So basically then my x will just be a single point. But we will go later to this. Okay. Good. Are there questions to this? Good. Then next thing I want to say is something, just some generals about why stationary, what this stationarity is kind of good for. And then later some nice properties also of boundaries. And then further later, I will talk about the maximal boundary, which is the Poisson boundary, and which is a beautiful object and why it is beautiful. Okay. So stationary. Okay, first, what I already mentioned, but just to have it really written down, if we have that, if nu is G invariant, meaning that for every G in G, we really have G nu is the same as nu, then automatically we get that nu is mu stationary. Well, why is it? Just look at the definition. The G disappears in the integral and I'm not integrating over anything. Okay, so another nice thing is that whenever we have X is compact metric, then we always have that there exists a mu stationary probability on X. This is a nice and powerful property. Sorry, and G is acting continuously on X. So this is a nice advantage of this theory because invariant probability measures, they might not always exist. Yes, we have seen a nice characterization of amenability, meaning that, okay, if you have the group is amenable, then you can always find an invariant measure on every compact, for every action on a compact space. But in general, sometimes there are invariant measures, sometimes they are not. But for stationary measures, we can always be certain they exist. And the proof is actually not difficult. Namely, we just have basically to observe one thing and then to apply Markov-Kakutani. Namely, there is a map from the space of probability measures on X to the space of probability measures on X, which is just nu is mapped to mu convolution and nu. This is a nice map because it preserves the convex structure, meaning it's a so-called affine map. This is affine. We do know that this probability space, this is convex. It's closed, compact. Since X is compact, the space of probability measures, it's compact. Well, it's non-empty, and therefore we can apply Markov-Kakutani. Again, as Bakir said, often in probability we apply it just for single map. Markov-Kakutani in general is for having a whole family of maps which commutes. But in this case, we just take one map, namely this map. And Markov-Kakutani says there exists a fixed point. Well, what is a fixed point for this map? It's just a stationary measure. And that's it. So I told you before that the kind of people working in invariant dynamics, they are in fact working in stationary dynamics, but I tell you, people in stationary dynamics, they are actually working in non-singular dynamics or also quasi-invariant dynamics, how Bachir has told it today. So another fact is that if we have mu is mu stationary, and again generating, and mu is generating, then we have that G nu is absolutely continuous with respect to nu for every G in G. So this is also called non-singular or quasi-invariant. So meaning that it does not preserve the measure, but it preserves the measure class. Okay. Again, the proof is quite easy. Let's just do it because it's a winter school. So if we have some A which is measurable, with nu of A being 0, what do I want to show? What do I need to show for the proof? Exactly. I have to show that this G nu of A is also 0. So I look at, okay, so to show is that the nu of G inverse of A is 0 for every G in G. So, okay, we know 0 is equal to nu of A, but we also can write it just by the stationarity equation here as the integral over G of nu of G inverse of A d mu of G. Well, but if the integral is 0 and I know that all these things here, they are non-negative, so I know that at least for mu, almost every G, I have that nu of G inverse of A is equal to 0. And then I need to now use that the mu is generating, and this kind of completes the proof then. Okay, I mean, there is still something to do, but it's you can do it. It's not difficult. Okay, okay, so this was something about just stationary dynamics. Let me just mention briefly something about boundaries, and let's then have a break. So some nice properties of, where is it? Should we have break now? Yeah, it's okay. Some nice properties of boundaries. Of let's say G x nu being a mu boundary. So one thing is that every mu boundary is ergodic. So it is ergodic, meaning, does everyone know what ergodicity is? Yeah. Who doesn't know what ergodicity is? People are tired. Okay, so this means that whenever we have, so if we have some measurable set A such that GA is equal to A for every G in G, then it follows that nu of this set, so if I have an invariant set, the nu of this set has to be either the full universe or nothing. Okay. Second property is that at least if G, let's say G discrete, so if G is discrete, so countable, then we do have that X nu is atomless. Meaning that nu of a singleton has always to be 0 for every X in X. Okay. And so this should I, yeah, maybe this would be also exercise. I know people don't do exercises, but exercises prove this. Maybe a hint for this exercise would be, okay, assume this is not true. Assume I have some element which has some strictly positive value. Take this element to be the maximal one and derive a contradiction. Okay. Third property is that, so in general, if you have some, let's say if we have X and nu, let's now take some different notations maybe. Okay, let's just say if we have that nu1 and nu2 are ergodic probability measures, in general, it's not true that the product will be ergodic. This is in general. But for boundaries, it is true if I take an invariant probability measure, which I'm kind of taking the product with. So sorry, this is still free. So if I have that X and nu is a mu boundary, and I have that, let's say Y and M is a G invariant, so G acting there is measure preserving, or let's say G invariant was the term I used before, and ergodic. Then I have that X times Y with the product measure is ergodic. Okay, so this is also some nice advantage of boundaries. Okay, maybe this is a good time to make a break because I will skip the proofs for this anyhow because of the time. But let's make a break now and then let's resume 10 minutes after half. And then I tell you something about harmonic functions. Can we start again? Okay. So now I give you a kind of different approach to these boundaries, namely via harmonic functions. So the definition, a function h from the group to, let's say, R is called mu harmonic. Again, mu is our random walk on the group. If it fulfills the following mean value property, and also for this we need that h, if whenever I move it with an element in G, then this should again be a L1 function for every G in G. And I want to have that G at an element, so the function at an element G should be the same as if I move my G by some G prime element and I'm averaging over all G prime of the group, then this should be the same. This is sometimes also just denoted by mu convolution H. In this case, it would be at the position G. So what does it mean? It's maybe looks more scary than it in fact is. Let's go back again just here shortly for the free group. So what does it mean? It means that if I have some value here, it should be the average of the values surrounded by. So for instance, if I have here, I don't know, -1, and here I have 1, and let's say I have here 1/4, and here another 1/4. So what then I want to determine now what is the value here in the middle. So I have to take, again, if I have simple random walk on the free group, then I have here, so I'm averaging over my random walk, meaning I have 1/4 times, and then whatever values this function takes here. So I have here 1, -1, 1/4, and 1/4. So in the end, I get out here, it should be so 1 divided by what, 16? Oh, no, well, this would be 1, sorry. Yeah, calculating. It's just 1/4 again. So this means that there is always, when I say to non-mathematicians that I'm a mathematician, and they say, oh, you can calculate, and I say, no, I can't. So this 1/4 here means that here I have to put 1/4. Okay? If I put it there, then this would fulfill this condition which I have here for the harmonic function. And again, the harmonic function, it's going from G, so in this case from the free group, and at each of the elements in the free group, it would assign a value. And we don't look at general harmonic functions, but we look at bounded harmonic functions, which we will denote by G infinity of G mu. This is the collection of all bounded and mu harmonic functions. Okay, so what's now the relation of these two boundaries? Well, if I have that G is acting on X and mu, and this is a mu boundary, then in fact, I can kind of take all my L infinity functions on this space and embed them nicely in my bounded harmonic functions. Namely, then we have that the L infinity functions on X and nu, they sit inside the bounded harmonic functions on the group. So in namely, more precisely, how do we do this? In fact, we do have that we have a map T nu, which is a map from L infinity of X and nu to the harmonic functions on G and mu, which takes some element f and I map it to P nu of f. And how is this P nu of f defined? Well, I just take the integral of f of, and now, I mean, this should be a function on G. So I want to make here space for whatever my G element will be. It will act on my entry x, and I'm integrating over all entries x over x. Okay, is it clear what I mean with this notation? So this is a function on G. Whenever I put the G here, then the G will be here. Yes, just a space holder. This is called Poisson transform. So for some reason in my preparations, I was writing Fürstenberg transform. So I mean, all this theory, which I will write it down in a moment, goes back to Fürstenberg. But I don't know if people call it the only Poisson transform or also Fürstenberg transform. And this is a nice map from L infinity to H infinity. And in fact, we have P nu is of f is mu harmonic if and only if actually the nu is mu stationary. So just to define this map, I don't need that it's a boundary. I don't need anything. But to have that it actually goes to the harmonic functions, I really need the stationarity. And then the proximality of the boundary gives me this, actually, this is an injective map. So we really have some nice embedding. Maybe just, but time-wise. Who wants to see the proof of this? No one. One person. Okay, one person is good enough. So proof. So let's just say if we have that this is if P nu of f is mu harmonic, and we will see we can just reverse this proof just the other way around. What does it mean being mu harmonic? So it's a good exercise to just learn the definitions. So what do we have? We have that P nu of f at some element G. This is a function at G. This should fulfill this averaging property, which we have written on the top of the board. So we have here, this should be P nu of f of G, G prime, d mu of G prime. So what does it mean then? This means here that we have here the integral of G of the integral of x. Now I put in the definition of f of G, G prime x, d mu of x, d mu of G prime. But what do we have written here on the other side? Well, here we have written the integral of f of gx d mu of x. And what is this here? Well, this is basically multiplying the x element and integrating over all the g's, which is basically what we had as the definition of this convolution of mu and nu. So here on the right-hand side, we have actually written the integral of f of gx, and here d of mu convolved nu of x. But okay, so this is true for every L infinity function. So this actually then just means that nu has to be, yeah, actually you can also take the identity here. You don't have to take the G, whatever. So this means that nu is this. Okay, and you can read the reverse proof the other way around. So actually here in the very beginning, you can just take the identity if you want to. I mean, just take here identity. Then you see this. Yeah. And reverse is just similar. So this means that really this if we have something stationary, we get something harmonic, and if we have something harmonic, we get something stationary. So this is this last equivalence, which I now proved. And then, as I said before, let's say nu being mu proxima implies that actually this p nu of p nu is injective. So we really actually do have that p nu gives us a nice embedding of L infinity of x nu to the h infinity of x and of g and mu. And this means we have some nice inclusion. Okay, so we do know now that L infinity of x sits inside here. And the natural question which you would now ask is, but okay, when is it equal? And that's exactly the Poisson boundary. So it deserves a new blackboard because the Poisson boundary is very important. So the definition, which goes back to Fürstenberg in the 60s, so he developed all this theory, is that there exists a unique space and group action such that really we have the L infinity functions on this space are isometrically isomorphic to the H infinity functions of G and mu. So it's really an isomorphism also in the level of algebras. So you can have here just pointwise multiplication, and here you can define some nice multiplication which preserves the harmonicity. It's about taking limits. And this then this nice Poisson map actually is really an algebra preserving isomorphism here. Okay. Good. Yeah, maybe okay. And then it is called so x nu, let's say, okay. G acting on x nu is then called the Poisson boundary of G with the random walk mu, and this is denoted by, I will just denote it by poi of G and mu. Other people write some big pi, but maybe then it's confused with products. And the very kind of one question which you should already now interrupt me and ask, what do I mean with unique? Unique in what sense? So what do I mean with unique? I mean up to isomorphism and null set. So I am allowing that I can have some space which is up to a null set isomorphic to this space. And okay, so it's just on the measure theoretical or on the measure theoretical level, this is unique. Okay. Are there questions to this? Yeah. Exactly, it's a surjective, and it also preserves actually the algebra structure on this thing. So maybe it's even worth to kind of write it down. So this is, so it means that P nu of some F1 times F2 is really the same as P nu of some F1. And let's denote it like here, this P nu of some F2, where this is some nice product. I mean, kind of a way to put a product on the harmonic functions, which still is harmonic. In general, pointwise product would not be, but if I convolve it with mu often enough, then it will be. So this is just by definition, this is the limit of mu convolved n, convolved now in this kind of function way of P nu of F1 times P nu of F2 for n to infinity. And yeah, this kind of this P nu map here, P nu is a isometric isomorphism. And now you have to ask me, okay, now you say Poisson boundary, and before you said boundaries, so how are they related? Is there a relation? So in fact, what you also can say equivalently, equivalent definition of the Poisson boundary is that the Poisson boundary is the maximal. I will say in a moment what I mean with maximal mu boundary. Maximal in a sense that so with respect to G factors. I will explain, I give the definition in a moment. So what is the picture which we have in mind is we have here the Poisson boundary of G and mu, which is some nice measure space. And downstairs we have some other y eta, I don't know, some c theta, whatever. And all these are kind of nice G factor maps. And the Poisson boundary is the maximal one. So I cannot have something which, so all the boundaries which are introduced, all these are the mu boundaries. Mu boundaries, they will be factors of the Poisson boundary. So is everyone familiar with the notion of a factor? No. Good. So let's, do I still? Oh, stop. So definition, if I have so G acting on some X and nu, is it clear that there's, so yes, okay, I have so. So this is really this kind of, with that, when I write poi of G mu, I really mean this is some X and some nu and G is acting there. Yeah. This is, and I have some G acting on some other nice space. Y and eta is a G factor. If we have, there exists, let me write it a bit. There exists some pi from some x0 to y0, where basically this x0 is x up to some nice set modulo nu, and y0 is y modulo eta, and of course this is measurable, and such that the map is G equivariant. Meaning that we had this in the beginning, but maybe just repeat it. So G acting on some X is the same as G acting on pi of X for every G and for almost every X. And we have that nu is, if I push forward the nu with my map, so let me write it by pi nu, this is just eta. So, and here again, this pi nu of some A is just defined to be nu of pi inverse the pre-image of this map of A. Okay, this is the definition of a G factor. So there is a nice map from this space to this space which preserves the G action, which is nice with the G action. Yes, I'm looking at I'm looking here at boundary actions, which are always non-singular, but yes, you're very right. So, but yeah, yes, so maybe I should write here that this is non-singular. Okay, good. So maybe, okay, then maybe as a small observation, the G factor of a boundary is always a mu boundary. Okay, so this really makes sense to talk about factors. So whenever you have a mu boundary and you take a factor of it, then it will also be a mu boundary. Yes. Sorry, yes. Yes. If you take any G factor of a mu boundary, it will be a mu boundary. And what next? Yes, let's just denote some interesting properties of the Poisson boundary. So whenever you have a normal subgroup, then you will have the Poisson boundary of G and mu factors to the quotient with respect to this normal subgroup. And here you just have a measure, just a projected measure down for the coset space. So this is one thing. The other thing is that the Poisson boundary behaves nicely with respect to products. So if you have really product of mu1 and mu2, this is the Poisson boundary of G1 and mu1 times Poisson boundary of G2 and mu2. And another interesting thing which relates to the lecture in the very morning is that the action of G on its Poisson boundary is always amenable. So it's always amenable in the sense of sigma. Okay. Good. And not the group is amenable, the action is amenable. Yes. No, I mean, you want to have the random walk generating, admissible, I mean, spread out. So this standard assumption that you can even kind of have the action of for locally compact second countable groups, the action is always amenable on the Poisson boundary. This is a result of Simmer. There is a paper of Simmer. It's called, I think, induced action and amenable, I don't know. And there he constructs that, gives a kind of nice way of a nice application for amenable actions. And this is the Poisson boundary. Yeah. I mean, you want to have locally compact second countable group. This is anyhow what we always have. I mean, I think you can also say it's this kind of what people call baby Simmer amenable, like kind of that you have this equivariant map. This is also true for this setup. Yeah, but I want to talk about trivial Poisson boundaries also a little bit. Time is running a lot. Just okay, then still example. I take C. What is the Poisson boundary of C? Let's say also with simple random walk, but doesn't matter so much. So also with, say, with probability 1/2, you go here or here. What is the Poisson boundary of C and mu? So I showed you that, or said that Poisson boundary has something to do with harmonic functions. Now try to put here an harmonic function. You can do it, but try to put a harmonic function which is bounded. What are their bounded harmonic functions on C? Yeah, exactly. So so the bounded harmonic functions on C and mu are just the constant functions. So this means that the Poisson boundary, in fact, is really trivial. And so it's more general, is that whenever you have G is amenable, abelian, then it follows that the Poisson boundary of G and mu, for some generating mu, of course, is trivial. Just 1 point. Okay, I mean, let me just denote this by just not writing Dirac measure all the time, but just 1 point. Okay, and I was actually planning to prove this, but this will be okay. Well, I prove it and then we do some properties later. Do you want to see the proof? Okay. I mean, Shokadini is more. It's more, but yeah. But yeah, I wanted to go to Shokadimi and the result then of being equivalent to virtual nilpotent and so, and equivalent definition of G amenable, which would be also nice. But maybe let's do this next time in more thing and just let's do the proof. So we want to show that because the proof is really not difficult, that just the bounded functions here are just the constant ones. So what do? We take some H, which is there, and we assume that this is extremal in the set of all these bounded harmonic functions, where I additionally assume that the norm should be, it should be bounded between 0 and 1. So this is a nice convex set. And so by Klein-Millman, it's enough to just look at the extremal points, because if I take the convex closure, and I have already shown that the extremals are all constant, and then I take the convex closure of constant functions, I will still have something constant. So it's enough to show it just for the extremal. So this is enough by Klein-Millman. So what do we have? We have G is harmonic. This means I have, this is written as G prime d mu of G prime. And now I use that it's that I have an abelian group. So this means that instead of here having G and G prime, I can write here G prime and then G. Okay, but now I claim that, well, H and composed with this G prime, this is again a function in let's call this set maybe K. This is again a function in K. One can show it's not so difficult. This is again harmonic. And of course, I mean, the norm is clear. So this is again a function in K, but well, we had something extremal. So this means that actually H has to be equal to this thing. So we have, this has to be equal to this one for almost every G prime. Well, but yeah, but this means that it is then, to just use the generatingness again, so we get it for everyone. This means then that H is constant. And this proves the claim. Okay, and I'm already over time. Okay, but so, okay, the next time we will see Choquet-Denis and nice characterization of a group being amenable in terms of the Poisson boundary. And then we will go a little bit to commensurated subgroups. Okay, so thank you.
Okay, Thomas, I'm allowed to now stop the recording.